Hello. Hi, welcome to the panel on future directions and applications in communication networks. Some of you may know my father-in-law. He was a long-time professor in EC, Illinois. And when he found out that I was going to Jean Walrand's retirement, he said, "He's a kid, why is he retiring?" I guess he's a bit older. I was trying to think when I met Jean, I think it was at a communication networking conference in the early to mid-90s. I think it was around 1994. And I was trying to look up on the internet. It was a time when Jean gave a plenary at this conference in Boca Raton, which they used to hold around the time. And it was so long ago that there's no information about it on the internet. So even though it's been only 25 years, it doesn't seem like that long, but I guess it predates the internet. So I heard Jean talk for the first time there. And before that, my idea of a talk was, I thought the whole idea of giving a talk was to confuse the audience. And here there was this brilliant person getting up and giving a talk that was outstanding in depth, but also understandable to everybody. And so that was an inspiration to me. So you've been an inspiration to me, Jean, in many ways, not just giving talks, by your work. Jean has always been at the cutting edge of research. I remember when I was in Bell Labs, there was a lot of work on trying to understand what are the benefits of moving from a circuit switch to a packet switched network. And a lot of people there were reading Jean's work, along with those of co-authors here, on large deviations. And later, when I started working on internet congestion control, Jean introduced this notion of alpha fairness. And later on, again, in the area of wireless networking, Jean, I think Kumar already mentioned that, introduced this idea of CSMA combined with queue-length information. So Jean has always been a leader in telling everybody else what one should work on. And so today's panel is supposed to be future direction. So maybe one way to interpret it would be to try to figure out what Jean will be working on for the next 30 years. So I have put together three wonderful researchers in our area. So Mohammad, Alizadeh, Balaji, Prabhakar, and Pramod, Viswanath. So each of them will give about a 3-minute introduction to what they're working on right now or what they think are great future directions in networking. And then I hope to involve the audience and hope it'll be an interactive session trying to figure out what are some interesting trends in this area. So I invite Mohammad to first give his 3-minute pitch.
Is this working? Okay, thank you. Yes, I will. First, John, congratulations. It's really an honor to be here. In 2013, when I was just going on the job market, I remember John invited me to give a talk in his group, and he gave me a ton of very useful advice. I'm very grateful for that. So what I wanted to talk about very briefly is actually related to the discussion we're having at the end of Andrea's presentation, and that's that in designing network systems, we often face this tension between optimality and universality. And I think machine learning has a role to play in kind of breaking this tension. And it's one of the sort of the big areas and promises of machine learning in networking. So that's what this picture is supposed to show. Here, in this box, on the x-axis you have universality. So you have environments that are either very heterogeneous or environments that are homogeneous. And the y-axis you have performance. And if you look at sort of classical approaches to network control, they're really about these two corners of this box. If you look at internet protocols, like the TCP transfer protocol, they're really achievements in designing sort of for very universal conditions. TCP works in an incredibly wide range of networks. It's not really optimal in any of them. And there's a lot of research on kind of specializing TCP for different types of networks. This kind of classical approaches have been very fruitful in environments that are homogeneous. We have very good models for them. And for example, in data center networking and data center transport, over the last decade, we've seen a lot of work on designing very specialized protocols that perform extremely well. What's missing from this picture is this remaining corner of the picture. And I think this is where machine learning has a role to play in the future. It's really about, can we use data-driven techniques in machine learning to augment network protocols so that we can design networks that can adapt to very heterogeneous conditions without sacrificing optimality. And so in my group, recently we've been working on a number of systems that use machine learning, particularly reinforcement learning techniques in the context of network control, and we try to learn network protocols that are essentially learned through experience. And I just want to give you one example of that that we've recently been working on, which is a scheduler for cluster computing systems. So this is a system that's designed sort of for a very general case. A lot of systems in data, a lot of data processing systems represent jobs as DAGs of stages. So you have these jobs that come in. For example, think of a system like Spark. There's processing stages. That's what these nodes are. And you have dependencies, data dependencies between stages. So for example, a node cannot start until all of its dependencies are met. And these kind of systems give rise to very complicated scheduling problems. So it's kind of an example of, not NP hard, but NP really hard that Andre was talking about. And we've been building a system that can learn how to solve these problems, essentially using reinforcement learning and through experience. So just as an example of what this looks like, this is sort of a Spark visualization of Spark running 10 different jobs. These red lines are the completion events of the jobs. This is before we've trained our system, and as you train the system, it learns better and better scheduling policies. And eventually it learns policies that actually we don't really know how to beat. I mean, it's about 2x faster than the best heuristics that we have for this problem. This is an example of a problem, again, that we don't have really sort of optimal algorithms for. Obviously, I'm going to keep it at a very high level. I won't have time to go into details on this, but I'm happy to talk to you more about it. So I'll stop there. Looking forward to the discussion.
Thank you. Balaji.
I want to start by saying, Jean, first time we met, I was a postdoc here for about the 1 quarter between finishing up PhD at UCLA and then getting to go to UK for a postdoc. And we had Nick Bambos, I'm your grandson, a great grandson. So the tree in this case is rooted at Praveen Varaya is like very fertile. I see a lot of people here, right? So Praveen's like the Chengiz Khan of networking. More than half the networking researchers are like coming out of the Praveen genetic pool. Okay. So anyway, happy to just share a few things that I actually learned from Praveen and Jean long ago. Because I was a late entrant into networking. In the PhD sense, I was more a control theory guy working with Balakrishnan. Then Nick came to UCLA and I began to work with him. We all know this. I'm going to be brief about, there was telephony and circuit switching and packet switching showed up. It had this motivation of like, you must be connected regardless of the circumstances. You must make sure communication is possible. In the very early days, there were these two branches of communication and computation. That was, ARPANET, etc. And this side was the HIPPY. There were DARPA projects and NSF projects down this path, the computation path, the Multics system out of MIT and so on. One side thrived, and the other side sort of petered out, okay? Supercomputing was still the big thing on that side. And the reason I think was simply its best effort design. It was just when all you have to do is make sure things are connected, you don't really care. You're on the universality side, you're not really caring about the optimality. And so it was able to scale, and most importantly, it got all this commodity hardware going, whether it's the Cisco Junipers of the world or the server guys like Dell and so on the other side, computing side. Okay, and so fast forward to 2000, so the high performance side just kind of petered out and was difficult to scale, make them cheap. So this is sort of what it looks like. Decisively, Ethernet and Internet have won out. Mobile networks got added, and we slowly started moving away from communication networks to computing. It's arguable that there was nothing here to begin with. Now there's a lot of it. That's all of cloud computing is in here, for example. But the communication infrastructure used is still that. Okay, and so people have wanted to have, when you move from there to here, you're asking questions like, why isn't my network more programmable like my computer? And that led people to Nick and others to define programmability. Okay. And again, that's another Varaya Waldron tree. offspring, okay? The other Nick. So, self-programming networks is a quest for programs. That's what we're working on. So this is nice to know that they're programmable, but what are the programs, okay? So we want to make networks sense and monitor themselves and control and program themselves. So we think of it as a combination of engineering and design. The way you can think of it is, so it's not an accident. You're sort of trying to come up with a name for your project, and then you look around. Self-driving is the cool new prefix. So you just grab onto it. You use it however you want. It always works. Self-driving toothbrushes, for example, or anything. Self-driving shoes, whatever you want, okay? So it's a useful prefix. It's like turbo in the 90s. So if you take a plain old car and add sense and control to it, you'll get a self-driving car. That's our goal. This transformation costs about $20,000 odd. That's about 30% of the cost of the car in this case, roughly. You could also consider doing that to data centers, where you have a data center is processing some workload and supports some apps. If you add sense and control to it, you make it a self-programming network. I just need to tell you about where we're doing sense and control briefly, and we're doing it all at the NICs. Okay, so skipping ahead, what does that mean to sense and control of the NICs? So we're not touching the switches, we're not touching the servers. Okay, so you're sort of now in the world of tomography, which works in the case of data centers, because you're looking at transmit and receive timestamps of packets and then piecing together what happened inside the network. And since you're taking timestamps at different servers, critical is the use of clocks. You have to synchronize the clocks, okay? So this is sort of the motivation, and there's a whole bunch of things to say about, this is what we're working on. Is it a wave? At the moment, it certainly feels like a ripple. It could be a wave, who knows? But the thing we found immediately is that it's very interesting. So who cares about time? Financial industry does. There are different parts of the financial industry we found that need it. The way you need it, so think of a NASDAQ-like exchange. This is from the Deutsche Börse guys. It's very critical. The word fairness applies in this universe. And what it means is that if I submit a bid to the exchange, then my bid cannot be overtaken by your bid if your bid came after my bid, even though they came at different gateways. So it turns out with synchronized clocks, you can actually manage to resequence just before execution, and also on the outbound order book delivery side, so that nobody gets any advantage of seeing what the prices look like. You can also do it on the outbound side. So the last thing I want to say is this has been trialed, and there was this sort of front page story in the New York Times about it, and it was really about if you whittling this clock sync and why it's interesting for the financial industry. So Jean's heard me say this, describe it to him earlier. But hopefully this industry where high performance networks matters, and you're still already in the world of commodity networks and unstructured cloud-like environments, because these finance guys take great pains to make the latencies really small, there's some possibility here that the self-programming type work we're doing could be relevant. That to me represents an interesting opportunity. Okay, so thank you.
Balaji. Pramod.
I didn't mean to do that. Cool and all that.
Clockwork Orange. Yes.
This one's made by Apple.
No. Mine is not. Let's see.
All right.
Thank you.
Good afternoon. Thank you for coming to this session, and thank you for inviting me, the organizers. And most of all, happy to have met Jean. I met Jean in the fall of '96, around this time, 22 years ago. He was on my prelim exam committee at Berkeley. Clearly, I'm from the same tree, Praveen and Warren tree.
So did he ask about Hilbert's paper?
No, I know the question very well, actually. It's on Marko chains and stopping times in the strong Marko theorem. And I also know the question Venkat asked and Praveen asked. Those were my committee members then. Since then, I've been interacting with Jean over the years, in many, many roles. He's taken me to the music performances on Wednesday afternoons. It's been great fun. Thank you. It's really been a privilege knowing you, Jean. And I'm very happy to be in this panel. I'm working on blockchains in the last couple of years. I've had a few students graduate. We've worked on a variety of aspects of blockchain. Some of them maybe getting open sourced into Bitcoin Core. We've been working on blockchains, and I think this is my title. It's really just exactly for this society and this community and this room, basically. It's EE systems in the real world. So that's that. But I just want to say there are three things here. I don't need to define these things here for this audience. That's good. But the other part of the equation is what are blockchains, and there's plenty of bubble. It's a bit ironical that I have to explain beyond the bubble. I think I saw this last year on Highway 85. A bumper sticker saying, "Dear God, just one more bubble before I die." And I'm here in the Valley, so I'm here on leave doing a startup. But I do want to think outside the bubble. And I think blockchains really are at the core of some force beyond the bubble. And maybe temporary, it may go and come, but it's something that advances the genetic and evolutionary advantage of humans as a race. I mean, in well-known biologist words, the evolutionary advantage of humans as a species has been that you can cooperate, A, B, flexibly, C, in large numbers. And historical modes, this notion of trust, and you can do trust in a flexible, large number way, scalable way. And historical nodes of trust used to be tribal communication. Hey, you look like me, we have the same skin, same facial expressions, and same language, so we have trust. And then that evolved into institutional cooperations, and the trouble with that, of course, is that power is at the top, and of course, corrupts. And blockchains really are along this line of trust. It's a way of getting distributed trust. And anything that pushes such a basic evolutionary advantage of humans will not go away, not just be a bubble. And the fact that you can do this cooperation in a distributed way was already demonstrated by Bitcoin about 10 years ago, right? Exactly 10 years ago at the peak of the financial bubble. Bubble and crash, just about the crash time is Bitcoin came out. The fact that you can do it flexibly was done by Ethereum 4 years ago by that notion of smart contracts. So it's not just currency, but it's a programmable currency. So you can do it flexibly. The biggest challenge that where blockchains are is the third part. You can do it in large numbers. In other words, scalability. Take it to man, woman, child, and planet. And that's what I've been working on. I think much of the community in blockchains wants to work on it. There isn't that much of an overlap with academics. So the course at Berkeley I heard was on blockchain to start by 2 undergraduates late in the evening, last spring. So it's hasn't had much of yet work in the academic community, but I think it should change, and part of this panel is I'm evangelizing a bit for that. And the way I want to evangelize is by saying that it's really at the core of it, especially when you want to scale, is a mixture of networking and incentives, which if I take these two titles and variants of it, it's probably 50% overlap with many people's CVs. So, I mean, it's at the core of what we do. And there are two types of networking problems. One is what we would say on-chain networking. So this is a peer-to-peer network where your basic primitive is broadcast. I want to tell everybody something. Something usually refers to a transaction I made if it's a cryptocurrency application. And the trouble is that because it's distributed, different people hear at different times, and the ordering is off. And this notion of asynchrony, if you wish, and the difference in timestamps at which when it was done and when it was received, and different people have different views. The blockchain world has a name for it. They call it forking. And the ways to sort of address forking is sort of you can do it. One way to do it is what traditional blockchain methods have done. Bitcoin, they try to have a specific way of breaking the fork choice rule. So if you have a fork, then you follow the longest chain. So that provides some way of cutting down this fork. But it reduces throughput because all these other things are dead and they will come back, get renewed, and they're orphan blocks. The other way is to force synchrony. And this is another different approach. You might know about Algorand from MIT, Stellar from Stanford, but they increase latency. I mean, things have to slow down. But the heart of it is really you can perhaps do something at the network level. Both of these are algorithm level, that are higher level ideas to reduce forking. But perhaps one can try something at the network level. And that's something we've been trying. So for example, here are three different people. They have a view of the blockchain. And they're all not the same. And there's a global view, which none of them have. And now if somebody wants to propose a new block, which is a group of transactions, then perhaps this guy is the proposer, and the global tree knows where it should fit, how it fits in, but it contradicts how these guys look at. And one possibility is that just before proposing, it's a broadcast method, maybe you should poll a few people, get their view, local views, and update your view, and from there build on top of it. So if this sounds like there is some power of D choices going on here, and it's actually it is. And so one can prove theorems about it, except this time you're not joining the shortest queue by polling B, you're joining the longest queue. And the asymptotics are all about how large the largest one is. Because it's not load balancing, this is information balancing, and the way you do it is by having as few balls in any of the bins except one. And and then there is something specific to blockchains and something actively being worked on by many blockchains called proof of stake. That's the kind of challenges that come on-chain networking. So I wanted to say, hang on. This is collaboration with Julia Fanti, who's known to many people here. She's on leave working full-time at our startup. And Jian Tao, who's a professor here. And my colleague Sevung Go from Illinois. This is one type of networking. Another type of networking is what one calls off-chain. And the idea is that instead of having everybody work on-chain, even if you're going to buy a $5, we bought it for $8. Yeah, I'm still thinking of the $5 lunch I used to get in '98, but it's $8 today. But on Telegraph, where that you already have made some. It's like a gift card with a merchant that you already have. You already have put in some escrowed money, and maybe when you go visit it, it's a much easier way of trust because you already have it. But if it's the same merchant, that's good, but you don't have with every possible merchant. That's too much money to go and escrow every time for something that you don't use. So perhaps you want to route through other people to get to the merchant that you've not done. So these are called off-chain networks. So every time you want to make a transaction, you use these escrows to do it. And the key challenge is you want to do these routings in a way that it doesn't deplete balances along the way, and perhaps with the least amount of escrow. And these are called payment channels within the notion of, and this is considered for a wide way of really scaling the blockchain. Instead of doing everything consensus, and for each transaction, something should be taken off. And so the idea is that you already have, and then you can just, once you've already committed something on the block, then it's like a gift card between these two people. And now you can have a network of these people. Oh, I didn't realize that animation. then they can go back and forth, and these heights reflect what the imbalance is. How much I have paid on one direction compared to the other. Notice that there's a conservation, and you want to maintain this balance. And payment channel networks, you have to find a way through this path, through the balances, so balance should be large enough along the way. And the way routing is done is through source routing. You try to find paths from the source, and you find a series like this that works, and then you find a circuit, in other words, to go do it. But really, that's old school networking. For a networking person, this is kind of naive to do circuit switching, source routing. And we have packet switching, and a whole variety of work which are incentive-driven, distributed routing and transport. And one should exploit really decades of work of bringing tried and tested true networking principles to another area. This is joint, and we built something called Spider, so maybe, yeah, so it's a packet switch network, which is balance aware. And this joint work with Julia again, and Mohammad Alizadeh, who's here. So really, the startup we're in is a research startup, and if you are ever in the, many of these people, all of the people are collaborators at various levels, some working full-time on leave from their universities, some part-time, and some are collaborators. So if you're in the Palo Alto area, you can join me and David. We are working off this garage, and our team members. And I'm looking forward to the first panel. Thank you.
So I guess turn it over to the audience. If you have any, trying to explore questions of what is the new networking problems and so on. Pramod.
I could take this off, right?
Yeah, you can take it off. Yeah. So, are there any questions or comments? So maybe I'll start off by asking Balaji, for example. Or all three of you, I guess. What are some fundamental differences between how the internet works versus data centers? I mean, data centers are also have lots and lots of computers. Maybe not as many as the internet, but in the early days of the internet, probably there were just as many computers. So what are some fundamental differences between data centers and the internet, and also in how does it affect the way you do research, for example?
I think you wouldn't think of doing computation over the internet necessarily. You can, but you wouldn't. With data centers, it's primarily for computation. But it is supporting, of course, a lot of entertainment. I load now Netflix, Amazon Prime, all these guys. But I think the biggest difference is that. And I think that is an unexpected and really a massive success. And I think that success had to do a lot with the work mostly early out of Google, like Bigtable, BigQuery. Everything became distributed computation, databases, what are called pub subsystems, publish, subscribe. So I think this is like a huge revolution. I think the systems side of CS took over and embraced that whole distributed computation, the facilities available in the cloud. I think that's the big difference. Communication versus computation, and then every kind of aspect of computation got, like storage, everything got in there.
Yeah, I think that's spot on. The biggest difference is in the kinds of applications that people run in data centers and these distributed computations. I mean, the infrastructure itself is different. The networks are high speed, low latency. The switches are kind of have different constraints. But one of the interesting things actually that I think it seems like it's going to happen is it's true that so far we haven't really thought of doing computation over the internet, but it's likely that we will have to think more about systems like that for a variety of reasons. I mean, there's just the amount of data that's being generated. There's 20 million cameras, I heard, in Beijing. In London, for every 7 people, there's 1 camera. Soon, every car is going to have a camera, and we're going to want to do inference on all of these, these like video streams. There's no way we're going to actually centralize all that data and do whatever computation we want in data centers. And so I think one of the interesting challenges is, can we think of these computational platforms that are not so centralized anymore and actually operate over the internet? And we think about, how do you balance communication and computation and things like that? Can we learn?
Mobile computing, cars are all computing.
That's right. And it was a kind of an area that, people thought about, peer-to-peer was supposed to do this and kind of went away with data centers. But in some sense, because of the volume of data that's being generated, at the edge of, our networks, and because of other reasons, because a lot of places have restrictions on whether you can take data, from one country and move it to a different country. So there's a lot of reasons why people want their data to stay local, and that's going to force us to think more about these systems that actually do computation over the internet.
Want to add anything, Pramod?
I think it's pretty eloquent here.
Okay. Any questions from the audience?
So I have a question, which has to do with tons of data and trust and computation. And my question is, what would it take so that I can trust the news that I receive better? Fake news. Right? You have many, many variations of the same item, and I don't even know what it means to trust that particular piece that I hear or see or read. How would you approach that question?
Among all the bubbles in the cryptocurrency space, one is called Augur, and where they're essentially trying to do these prediction markets, where you put money and it'll be sort of an escrow. And if you're caught lying, or if you're not getting to vote when you have to say your thing, then your money gets deducted from it. So it's like you put your money where your mouth is, and it's held in escrow until you're sort of proved right. And I think it's one thing is to do within mainstream markets and try to sort of decipher what is fake news, what is not. The other perhaps is to have it's all in the mind. I mean, what is fake is may not be so fake for the person who's creating it. And if enough people put their money into an escrow and say a certain view, then that's definitely being tested out today within the blockchain infrastructure.
So the Koch brothers would have.
Pardon me?
Koch brothers could influence what is fake.
No, my question is not how I inject.
Pramod.
If I'm a Koch brother, I can inject tons of fake stuff. My question is, as a receiver of this, is there any way, either socially or somehow or the other, for me to put the trustworthiness number on anything I read or see or?
So one thing that's happened is proof of work it is not, people have done this for spam, to suppress spam. You're not allowed to send emails unless you do some work, and the work is usually you have to blow some compute cycles somewhere. If you put that burden on news generation, that could stem a little bit. Whether it's still going to be quality, that's not obvious. The Wikipedia seems to work pretty well. It is information, it's not news, so there's a difference. There's less opinion, right? And so I think that's, even in the world of news, there are different viewpoints, right? There's right, there's sort of left and right sort of outlets, even classically. I think what's changed is just speed at which things are happening, and there's no seemingly easy way of stemming it right now. But I think if you go to a model where it's socially curated, like Wikipedia style, but then it comes to who's curating it. It's not, this is more fundamental, I think. It's more, the same incident can be viewed two different ways. There's not much anybody, both are valid in a way. So I don't have a better answer than that.
So my question is kind of stepping back. So I think Pramod's kind of presentation kind of brought up something, right? He said, this is networking. This is classic E-systems, your perspective, right? That's what this is. So I think the question is, if you had to, right now, kind of, from today's point of view, say, what is networking? Like, intellectually, today, not this historical thing. Could you say, is there something that can be said, like in a fresh view of this is what, do you think it's the, what you said is, plus the combination of incentives and flows of information, like, for all three of you, like, what do you think of today? What is that? What is the field? Intellectual. Should there be networking?
Yeah, no, there is. There's no question about it. I mean, you just sort of drive a 101 and you can see it. So it's not invisible. It's very highly visible. But I think the definition is less communication exclusively. It's much more computation oriented. It's seriously dominant. It's the amount of money that some of the computation guys are making compared to the communication guys is scary. It used to be when Cisco, the packet switching taking over from circuit switching in a way. I'm talking about revenue share, not everything. Is similarly happening now. Computation is taking over from communication. If you like, Amazon's like supposed to get $100 billion in just revenues from its cloud side, and they're all running towards that. It's the fastest growing parts of all these companies. I think that's happening, and that is, networking. But to your point, is it there? It's there. But what is it intellectual? I think it's less about just point to point anyone. It's more about this sort of what he was talking about, this DAG, that there's a common purpose for many nodes. There's some application, some job. And how can several nodes get together to do that common thing? That is the difference, I'd say, between when I was a student to now. We never asked that question. It wasn't part of the ethos. Distributed systems existed, but didn't really become like what networks were supposed to be serving. This move to computation has changed that. And I think it's quite exciting. There are many things that is going on there. Maybe you want to add something.
I think I have. Yeah, I mean, I think. I don't know if I have a lot to add. I mean, I think that it is really about this shift that has happened from communication to thinking more about what we're trying to do with this. What is the goal of the application, and that's like I said. I mean, that's certainly something that's kind of very central in thinking about how we operate data centers and how we design protocols for data centers. And I think it's going to expand to the rest, to the wide area, to all other networks as well.
One thing I wanted to say is that even though networking directly fits into something like blockchains, but they're at an informational level. For example, I have this thing called the information collision channel, and for packet collision channel you had Aloha, and I have a protocol called Mahalo, which is the second most popular word in Hawaiian after Aloha. It's at an informational level, and the ideas and the background of technical thinking.
So can you say a little bit more about that? What do you mean by information collision?
Now I got myself into a pickle. I think the different people have different views of the blockchain. It's a tree, right? And you would like to all of them to agree on some things. And having this agreement and the fact that there's forking, which is inherently caused by the distributed aspect of the networking problem, causes information collision. And you would like to come up with protocols that reduce it. That's one example I was showing was an example of that. And you may want to wait, have this breathe before you speak. Generally a good thing, and it's also good in these networks. I think they come back at another level. I mean, it's not directly a packet collision, but some information collision. And it helps the algorithms to mix with the networking.
It's more like a consensus problem.
Yeah.
So I think Kumar has a question.
So, I want to talk about privacy. Is there any way of using some blockchain or some way so that if I want to put some bug in the system so that it just kills all my information? Some way of killing the distributed system with respect to my information.
You mean just erasing your
Exactly.
at will?
Yes. So I have control over my information, but my information nowadays is all over the place, right? And it's a distributed system like a blockchain. Is there some way of reversing it for a different purpose?
This has come up in two ways that I know. One way is, the way Silicon Valley seems to ask this question is, how can I own my information so I can make money out of it? Okay, which hopefully is close to how can I destroy it? Okay. That there's like you are a portion of the shopping data that Amazon has, but so does everybody else, and so you need to be reimbursed for your thing that Amazon makes out of you, for example, because you're part of some collaborative filtering. I've seen that give the user a bit more control of their information, okay? Deciding what they want to provide, you know. Does it exist a solution? Not yet. People have spoken about it. The other one is mostly on social networks. And it's this sort of weird way in which things seem to like trickle out about oneself just by the mere fact that one is just reading stuff or, you know, liking stuff or what they're looking at. And or even what you're searching for on the web, you know, things like this. That is, you know, is really the GDPR, the European Union's, by fiat, at the moment is the way it's going. I mean, I'm sure you've had to go back and every site you're accessing now is asking you to carefully look at their privacy policy and approve. It's all been rewritten. Maybe that's the way in the short term. But it'd be a good thing. Maybe you want some, you know, program to accompany your data.
I've heard that there are companies, I think, working on this kind of a thing of like a social network that's sort of backed by blockchain and supposed to let you be in control of your data. I mean, I haven't sort of looked too deeply into like how do they do it? I mean, what's the underlying technologies? But it is built on top of you know, these kind of smart contract you know, technologies. So it is really a program that you get to see and accompany your data.
The question, Kumar, is that you want to do it retroactively, right? That means you've already divulged information,
absolutely.
but afterwards you want to go and erase it.
Absolutely.
Actually, I haven't thought about this at all. I mean, I've thought actively about doing it while you're producing data. That's dandelion and so forth. But really the whole point is it's out there in the public, and once it's there, it's there.
Tara.
So, Mohammad, you were talking about this optimality, universality. So, two questions, maybe one is easier to answer. Have you looked at the cases whether you can recover some of the solutions we know in the homogeneous space, and then and how good it was or how long it takes? And then also in universality, can you be more specific? Because I can think of universality in terms of allowing a lot of the interface, and that would require really opening up the you know, the hardware side to be able to provide that kind of control, versus universality in terms of the protocol structure. So do you have anything, can you specify a little?
Yeah, so I mean, in terms of you know, seeing whether learning algorithms can recover sort of things that we know, I've done things like that in my work where, for example, for scheduling problems, show that, you know, this learning algorithm will learn like policies like SRPT. You know, it'll learn, you know, I think Pramod is in a different context, you know, for communication, has worked on things where, you know, he shows that a learning, like an RNN can learn to decode turbo codes, you know, learn the Viterbi algorithm, you know, in some sense. So I think there's been a lot of work like that where, you know, we can, people have done things like that.
Like, I remember that Pramod, when he was talking about it, it required like really curating a particular kind of data to most informative examples to make sure that the data was not enough by itself to actually lead it to the right way. You know,
too many code words.
There, exactly. Yeah. So he was. So was there a similar thing that you have
so
to
in,
do?
Yeah. So in every one of these things, it's one of the things that kind of in the work that, you know, we've done, we've learned is, you know, you can't kind of treat the algorithm as a black box and just hope that, you know, you can like give it all the input data, you know, run some reinforcement learning algorithm, and then it will just like magically work. I mean, it's reinforcement learning at its core is pretty dumb, right? It's like, you know, run a lot of experiments, observe what happens, and then follow a gradient. So to get effective algorithms, you actually do have to think a lot about what's the right representation of that problem. You know, an example of this, actually, some work that we've recently been doing with Devabrat. We were actually, just as curiosity, we're wondering, you know, can you recover sort of switch scheduling, you know, problems? And so we eventually succeeded. You know, we can like have a learning algorithm that does max weight matching, you know, as good as the best max weight matching sort of variants that we know on switch scheduling problems. but we had to think a lot about how do we condense the representation to get things like that to work. So for sure, a lot of sort of domain-specific insights go into every one of these. But what's nice is, once you kind of have these nice representations, you get very flexible systems. So if you change something about your metrics, change something about the nature of your system, you don't have to like rethink your algorithms from scratch. You'll discover these algorithms as you go.
Okay, I know I don't have time to talk about Jean, but I just want to say that his ramification went all the way to Africa, and he was even there, and very much appreciated. But my question goes to Pramod. Africa is somewhere where trust to the institution is really an issue. And now blockchain is really raising a lot of hope that it can replace many things. But the problem we have there is infrastructure is not there in terms of computation, but also communication. The links are going up and down. So the off-network thing that we talked about, I think that it could help do blockchain in a resource-limited environment.
Yeah, actually that is exactly the title of a proposal that Dedya Jansavar here has been funding me at Illinois, which is understanding distributed trust in resource-constrained environments. Yeah, I think very much. In fact, much of the network-driven ideas I started developing on blockchains were driven by that kind of workshop. Well, that idea where you are inherently in a resource-constrained environment. Primarily, your networks are, let's say, wireless.
Okay, we should talk.
And last question, Rahul had a question.
So in the last 3 to 4 decades, it seems that there's been very fast innovation on various aspects of networks and networking technology, except maybe the last mile. So in the last mile, it seems that we're still using technologies and protocols that have been there for maybe 2 or 3 decades. So is that a problem, or is that going to become a problem? And if so, then what kind of innovation is needed or could happen?
Maybe Andrea can answer this question. Wireless components.
So are we going to replace, so it's not, I don't completely agree with that, because fiber is certainly advanced.
Well, there's an issue of economics.
Faster. Yeah, there's economics, and there's just logistics of laying fiber everywhere. So if the question is wireless going to replace all the wired network for the last mile? There's been waves of fixed wireless access pretty much every decade, and they've all failed. And when you look at what's really the killer value proposition of wireless, it's movement. If you have a fixed system, then wireless doesn't have the same benefits as wired. And so, and it's very fragile still. I mean, unfortunately, there's still the laws of physics, which don't necessarily come into some of the networking things, but you can set up a link that's a 10 gigabit per second link, fixed wireless access, and then something walks through it or drives through it, and then your link falls apart. So I'm a skeptic about fixed wireless access because it's failed every single time that it's come into play. And I think that we can do better. I think it would be cheaper and more reliable to try to use wired technology there. But the question raises a more interesting one related to this discussion, which is, you think about more broadly, communications and networking drove EE, right? I mean, a lot of the success of electrical engineering was in those two fields. And now we're starting to see both of those fields be viewed kind of as maxed out. Yeah, I mean, kind of, they're commodities. There isn't so much innovation left to do, and everything is moving to computer science. And so, I mean, is that true? I think broadening your question, are there real breakthroughs to be had? And I think there is in wireless. That's what I tried to present. But are there breakthroughs in networking? Is EE going to have a resurgence? Because to do all the stuff you guys are talking about, blockchain and computation, all this, we still need the hardware and the infrastructure to support it.
So that's a great question. I think the question is, where is E and where is CS and what's going on. I think it's probably the case that we've defined what these things are. And sometimes we've defined them a little narrowly, as happens. And it's clean when it's narrow, and it's clear what we're talking about. Like, the well-known communication diagrams and the control system reference diagrams. They're in the first chapter of every book. And that sometimes can limit too much. And it's just up to us to, like New York is a state of mind sort of comment. E is a state of mind. And we don't have to be boxed in there. I think there's another take I have on it. I've been trying, I'll throw it out there. It needs some refinement, but maybe it's somewhat true. I think fields in engineering that have lost touch with the consumer end up being like a back office, back end, thing. CS has maintained that touch and it's just thrived. Mechanical engineering was in danger of petering out and then took the design school approach, went directly in front of the person, the UI, or Stanford Design School, others too. I think the consumer frontier is just not worth abandoning. I think the mechanical Astro is reinventing itself with drones. How cool is that, actually, right? I think the problem with us is us being now EE. It's not a problem. It's an observation. No, I don't know if it's even true. But I think the consumer edge is just worth finding a touch point to. We had phones, but then we don't have operating systems. That's what makes those phones cool. If you had button phones, it's not that interesting. Mostly complaining about it, like you were saying on your own drive, I think that's probably where we need a touch point. Some clear, easily identifiable, and then we will thrive. And Costas was saying in the morning that this is not the sort of thing we like to do, because it feels too mercenary. I don't think that's right. I used to not be sure of what the business school teaches until I taught there. I can tell you what it does. It teaches decision making. That's all it does. A manager is someone who doesn't know anything except facts as are told to that person, and they have choices. They have to make a decision. That's all they do, over and over again. Okay? And they're good at it. It's like poker players. There's practice at it. Good managers really are good at this. And they don't have to be the guys who generate the facts. That's for engineers or build systems. I think that's, okay, I've said lots.
Okay, I think in the interest of time we should wrap up.